About 13.8 billion years ago, the entire cosmos consisted of a tiny hot dense ball of energy that suddenly exploded. That's how everything began according to the standard scientific story of the Big Bang, a theory that first took shape in the 1920s. The story has been refined over the decades, most notably in the 1980s, when many cosmologists came to believe that in its first moments, the universe went through a brief period of extraordinarily fast expansion called inflation before settling into a lower gear. That brief period is thought to have been caused by a peculiar form of high-energy matter that throws gravity into reverse, inflating the fabric of the universe exponentially quickly and causing it to grow by a factor of a million billion billion in less than a billionth of a billionth of a billionth of a second. Inflation explains why the universe appears to be so smooth and homogeneous when astronomers examine it at large scales. But if inflation is responsible for all that can be seen today, that raises the question, what, if anything, came before? Why did the universe begin in the way that it did, if indeed it had a beginning? To some, that leaves the door open for a divine creator, a great being who lies outside of time and space. But it could also be that asking what existed before the universe is a nonsensical question, like asking what is north of the North Pole. Although effects within the universe have causes, the universe as a whole may not need one. But that answer doesn't feel very satisfying, and the famous physicist Brian Cox can sketch out some possible scenarios. So if the universe is eternal, and it might not have had a beginning. If it's eternal, what place is there for a creator? Imagine that the universe we observe from end to end is just a drop in the cosmic ocean, that beyond what we can see, there's more space, more stars, more galaxies, and more everything, perhaps countless billions of light years farther than we will ever be able to access. And as large as the unobservable universe is, there are again innumerably more universes just like it, some larger and older, some smaller and younger, dotted throughout an even larger spacetime. As rapidly and inevitably as these universes expand, the spacetime containing them expands even more quickly, driving them apart from one another and ensuring that no two universes will ever meet. It sounds like a fantasy, picture the scientific idea of a multiverse, but if the science we accept today is correct, it's not only a valid idea, it's an unavoidable consequence of our fundamental laws. So there are lots of multiverse. Actually, in physics, one of them is called the inflationary multiverse, which is essentially what happened before the Big Bang. The idea of the multiverse has its roots in the physics required to describe the universe that we see and inhabit today. Everywhere we look in the sky, we see stars and galaxies clustered together in a great cosmic web, but the farther away in space we look, the further back in time we look as well. The more distant galaxies are younger and hence less evolved, their stars have fewer heavy elements in them. They appear smaller as fewer mergers have happened, there are more spirals and fewer ellipticals, which take time to form from mergers, and so on. If we go all the way to the limits of what we can see, we find the very earliest stars in the universe, and then a region of darkness beyond that, where the only light is the leftover glow from the Big Bang. But the Big Bang itself, occurring everywhere at once some 13.8 billion years ago, wasn't the start of space and time, but rather the start of our observable universe. Before that, there was an epoch known as cosmic inflation, where space itself expanded exponentially, full of energy inherent to the fabric of spacetime. Cosmic inflation is itself an example of a theory that came along and superseded the one that came before in that it was consistent with all the successes of the Big Bang and encompassed all of modern cosmology. It explained a number of problems that the Big Bang couldn't address, including why the universe was the same temperature everywhere, why it was so spatially flat, and why there were no leftover high-energy relics like magnetic monopoles. It made many distinct new predictions that could be tested observationally, most of which have been confirmed. However, there's also one consequence that inflation predicts that we do not know whether we can confirm or not: the multiverse. The way inflation works is by causing space to expand at an exponential rate. This takes whatever existed before the hot Big Bang and makes it much, much larger than it was previously. So far, so good. This explains how we get such a uniform large universe. When inflation ends, the universe gets filled with matter and radiation, which is what we see as the hot Big Bang. But here's where it gets weird. In order for inflation to end, whatever quantum field is responsible for it has to roll from the high-energy unstable state that drives inflation down into a low-energy equilibrium state. That transition and rolling down into the valley is what causes inflation to come to an end and create the hot Big Bang. But whatever field is responsible for inflation, like all other fields that obey the laws of physics, must be inherently quantum field in nature. Like all quantum fields, it's described by a wave function with the probability of that wave spreading out over time. If the value of the field is rolling slowly enough down the hill, then the quantum spreading of the wave function will be faster than the roll, meaning that it's possible, even probable, for inflation to wind up farther away from ending and giving rise to a Big Bang as time goes on. Because space is expanding at an exponential rate during inflation, this means that exponentially more regions of space are being created as time goes on. In a few regions, inflation will come to an end where the field rolls down into the valley, but in others, inflation will continue on, giving rise to more and more space surrounding each and every region where inflation ends. The rate of inflation is far more rapid than even the maximum rate of expansion of an energy-filled universe. So in very short order, the inflating parts take over everything. According to the viable mechanisms that give us enough inflation to produce the universe we see, there are many more regions of space surrounding our own where inflation did end and where inflation doesn't end right away. This is where the phenomenon known as eternal inflation comes from. Where inflation ends, we get a hot Big Bang in a universe of which we can observe part, the one we're in, very much like our own, but where inflation doesn't end, that produces more inflating space, which gives rise to some regions that will have Big Bangs causally disconnected from our own and other regions that will continue to inflate, and so on. This picture of huge universes far bigger than the megaparsec that's observable to us, constantly being created across this exponentially inflating space, is what the multiverse is all about. It's important to recognize that the multiverse is not a scientific theory on its own. It makes no predictions for any observable phenomena that we can access from within our own pocket of existence. Rather, the multiverse is a theoretical prediction that comes out of the laws of physics as they are best understood today. It's perhaps even an inevitable consequence of those laws. If you have an inflationary universe governed by quantum physics, this is something you're pretty much destined to wind up with. It's possible that our understanding of the state before the hot Big Bang is incorrect and that our idea's the multiverse? It may go well beyond physics and be the first physically motivated metaphysics we've ever encountered. For the first time, we're understanding the limits of what our universe can teach us. There is information we need but that we may never obtain in order to elevate this into the realm of testable science. Until then, we can predict but neither verify nor refute the fact that about inflation are completely wrong for this application. If that's the case, then the existence of a multiverse isn't a foregone conclusion. But the prediction of an eternally inflating state where an uncountably large number of pocket universes are continuously born and driven inextricably apart from one another is a direct consequence of our best current theories if they are correct. So what is our universe is just one small part of a far grander realm, the multiverse. While many things remain unknown, there are some ways to get to the multiverse, but to do that, we have to start with just the universe. By definition, the universe is all the things. It is the sum total of complete physical existence. If it's a thing, it's in the universe. But even with that definition, we can start to crack the door to other universes. One way to do that is to recognize that the universe is only so old, and light can only travel at a finite speed. Indeed, so there's a limit to what we can observe in the universe. That limit is about 45 billion light-years away. However, that explanation gives you a very weak vision of the multiverse. Actually, there's more to the universe than what we can observe. So there's more stuff out there, more stars, more galaxies, maybe even more intelligent creatures than we could ever make contact with. All of these things are in the universe but are definitely not a part of our own world. In the multiverse, our universe is merely one of an infinite chain of universes. Imagine a giant foam, like the top of a bubble bath. The multiverse is the foam itself, always growing and always creating new bubbles, with each bubble acting as its own independent cosmos. All of these bubble universes exist within the same framework of space-time. If you point your finger in any random direction, somewhere out there, past some unfathomably huge distance, is another universe, and beyond that, another and another. The bubbles will never interact.